Howdy everyone, my name is Griffin Furlong. I'm a professional engineer in the state of Florida, and then today we are going to walk through 3 PE exam problems from the Water Resources and Environmental Test. To keep everyone in the loop, starting effective April 1st, 2024, the Civil PE exam will now solely be tested on your specific discipline. With civil engineering, you have a few different topics. You have construction, transportation, geotechnical, structural, and water resources and environmental. So what they have done is if you take any test prior to April 1st, 2024, which it's kind of coming up now, that test will be based solely more off breadth and the discipline. Like let's say if you're in water resources, you might have maybe a statics problem or maybe potentially some sort of structural or transportation like horizontal curves, but now they've eliminated that. So whatever discipline you are taking, those are going to be the questions that you get, which I actually think that'll benefit a lot of students out there because, if you are, let's say, a structural engineer, I don't think you're going to be excited about doing Manning's equations or any sort of stormwater stuff, and vice versa with the water resources. But without further ado, let's dive right into some of these problems. So the first problem that we're going to walk through is what I consider an easier type of problem. If I were to say the difficulty level of this one, I would probably score this maybe a 4 out of 10 difficulty, 10 being just extremely difficult. So let's walk through it here. A steel pipe is reduced from 1 foot 6-inch diameter to a 6-inch diameter as shown below. The flow rate through pipe 1 is 5 CFS, and that's cubic feet per second. The velocity in feet per second through pipe number 3 is most nearly what? The first thing that kind of crosses through my brain when I see any sort of problem like this is always the continuity equation. Any sort of flow through this pipe, I automatically have to start thinking about this equation here. Now what the continuity equation means is that the flow through this pipe will always stay the same. However, the velocity and area will differ because as we notice here, the flow through pipe 1, 2, and 3 all have different cross-sectional areas. But if the cross-sectional areas are all different, that means that the velocities are changing because the Q equals the same. So let's kind of break down more kind of in simple terms what this means. So what we should know by now is that Q1 equals V1A1, which also equals V2A2 and also equals V3A3. Now, one thing about this problem that's trying to kind of throw us off here is they give us all of these lengths. Well, these lengths are thrown here to just give us a curveball, and that's what the PE exam will do. They'll try to give you some curveballs and sneak in information that you don't really need. We do not need any of these lengths. Lengths has nothing to do with the continuity equation here, Q equals VA. So as I read this, what are my givens and then what am I actually trying to solve for? So one thing that we do know is the actual flow rate through the pipe number 1, which is the 5 cubic feet per second. So we know the flow. Now what are we trying to solve for? We're trying to solve for the velocity through pipe number 3. Well, if we know that Q equals 5 cubic feet per second, and we're trying to solve for a velocity in pipe 3, I'm going to put my attention to this multiplication right here, V3A3. I know that I can equal the 5 cubic feet per second to the V3A3. We know what A3 is because that is given right here in this diameter of pipe in the green that I'm showing. So we know the cross-sectional area. If we go back to 8th grade geometry, when we have a circle, the area of that circle equals pi r squared. Now, one thing I think to kind of keep us on track here with units is I would really like to convert this inches here of that diameter to just feet. So that diameter is half a foot. So if I'm trying to solve for this area down here, we know that the radius is half of that half a foot, which is 0.25 feet squared. Now we get out our handy dandy calculator and we can start multiplying this out. I got 0.196 feet squared. So now it becomes an algebra problem. We know Q, we know A3, our only unknown now is V3, and this problem just became pretty simple. Let's rearrange this equation here just to kind of be pretty clear. So I'm going to say V3 equals this Q over A3. Now plug in our knowns. 5 feet cubed per second divided by the 0.196 feet cubed. And what do we have left over? I'm going to put my answer all the way over here in bold. We got V3. Let's plug it into our calculators. 5 divided by 0.196. And we get 25.5 feet per second. Now, does that match up with any of the answers in the problem? And it looks like it does in fact match up with D. So just to kind of give a breakdown of this problem, you know, whenever you get a problem that relates to a flow through a pipe with different diameters, the first thing that you should always think of is that continuity equation, which is the Q equals VA. The flow is going to stay the same throughout that entire pipe. Now the velocities will change dependent on the cross-sectional area. The velocity gets higher in that smaller pipe. Now a couple things they did to kind of confuse us is that they gave us this pipe 2 diameter, which I think they were trying to make us do some more work, when in reality we didn't really need any of those parameters for that second diameter pipe, and we definitely didn't need the linear feet of the pipe because that has nothing to do with this continuity equation. Now on to question number 2. A cylindrical tank has a diameter of 18 feet and is 16 feet deep. The flow rate through the tank is 200 GPM. The detention time, hours, is most nearly what? So whenever I think of these tank sort of problems, and anytime they throw out detention time, my head immediately always goes to flow, so flow rate, and they definitely gave the flow rate. So let's break down, you know, what flow rate means in this problem, and we can identify if there's any unknowns that we're trying to solve for here. So again, I think where I want to start is the flow rate through the tank. That's definitely where I want to start, because if we know that a flow, let me break this down simple, a flow is always a volume over a certain time. And again, just to put some units here, a volume, which in this case could be gallons, could be foot cubed. We'll get there for a second because the flow rate was given in gallons per minute. But a volume can be this foot cubed here over a time, which in this case, you know, could be hour that we're looking for. So if we were given a flow rate, a Q, and then technically we were given a tank with some details here with the diameter and depth, I think we're getting pretty close to finding the volume of what we need. Then all that's left is finding this T here, which is time. So let's break this down kind of, you know, simply. I like to kind of, you know, go high level first and just understand what even Q is, which is a volume over time. Let's try to figure out, you know, how to get this volume. So again, during the PE exam, I don't think you'll have time to draw all these diagrams, but I want to kind of break down what you should be thinking about, just to kind of, you know, touch on the concepts here. So here we have a tank that looks something like this, part of my drawing skills. And what is it saying? So it has a diameter of 18 feet. So 18-foot diameter. And then how deep is it? 16 feet deep. A volume is always an area times a length, because again, a volume is always in the cube, a cube unit, right? And if an area is a square and you multiply it by a length, well, now you have a cube. So we could definitely get this volume here in cube because we do know the area. It's a circle, right? It's a circle. So it goes back to kind of that previous problem. Let's break this down here. If we know the area of, again, this circle right here, and we multiply it by that length, we now have the volume of that cylindrical tank. So let's break this down. So A equals pi r. So we need r. So it's half of 18. That's 9 feet. And then we're going to square it. Now it's pi times 9 to the second power. So now we have an area of 254. Do we round? I'm going to round here. So there's our area. Now in order to get, the volume that we need, we're just going to have to multiply it by the length. So we're going to multiply that 254.5 times 16 feet, and now we got our cube. So let's multiply this out. So 254.5 times 16. Okay, 4,072. I haven't had enough coffee today, guys. Pardon me. So now we have our volume. Voila. We have our two knowns that we need. Now the PE exam will definitely throw you curveballs with units, and it's important that we understand unit conversions, because if we go back to what we were given a flow rate of 200 gallons per minute. So we have our flow rate, but now we want to put it in the units that'll actually help us out here. So let's go ahead and understand, and you'll have to go to the PE exam reference manual to get your unit conversions. But what I will say is, if you know this conversion from the top of your head, then you will expedite all your time on the PE exam. So what we should know is that 1 cubic foot equals 7.48 gallons. So I want to convert this volume to a gallon right here. So I'm going to take this up right here, and I'm going to convert this to a gallon. So in order to do that, I'm going to multiply, and since I want the cubic foot to cross out, I'm going to put the cubic foot down there and then multiply by the 7.48 gallons. And this is a lot of gallons, guys. So we're going to multiply that by 7.48. That is quite. So now technically we have what we need. And I think I'm going to erase some of this stuff here. And again, there's a million ways to kind of change the units in this problem. I mean, you definitely could convert your flow rate to a cubic foot. I'm just showing you just one way to do this problem, guys. Math, the beauty of math is that you can do a problem a million different ways. So we definitely have our flow rate, and that, I'm going to kind of break this down here. So we have 200 gallons per minute, and then we have a lot of gallons here. This is our volume. And then we have T. So since we're trying to solve for hours, I mean, let's just do this. Let's solve for T, for a minute here, and then we'll just convert it to hour. So in order to do that, let's rearrange this equation and have T over on the left side, and all we have to do is do an algebra problem here. We'll have gallon, which is the volume, divided by the flow rate. And now these gallons will cancel out, and we'll have a T in minutes. So let's figure out what this is. So let's divide this guy by 200. So let's see how many minutes we have. I am getting 152, and I'll just call it 0.3 minutes. Now, in order to get to hours, what do we got to do? We got to divide by 60, and so we got 2.54 hours. Should be our final answer. Let's double check to make sure that's actually one of the answers in the problem. And in fact, it is. It is A. Again, you're probably not going to have that much time during the test. You have about 6 minutes to complete these problems because you have 80 problems. And so, you're going to want to power through this in under 6 minutes. I would say that this is a fairly simple problem that you're going to get, but it's going to be a very typical problem that you're going to get. They're always going to give you some sort of tank problem, detention time problem. The real curveballs they give you are always about units and just unit conversion. I took a very long way of doing this problem, but I wanted to kind of break down my thought process of how you can break down the problem. Now, last but not least, we got problem number 3. A catch basin is to be installed adjacent to a 3.4 acre parking lot. The design rainfall intensity is 6.7 inches per hour and the runoff coefficient is 0.84. The peak discharge, cubic feet per second, to the catch basin is most nearly what? Again, understand your units. Always understand your units. They're asking for a peak discharge of cubic feet per second. Now, what else did they give here? Okay, actually, after reading this problem, and again, I haven't even walked through these problems yet. I'm just reading them straight on and writing them as I go. I know from a fact that when I read this question, I immediately thought of the rational method, guys. The rational method. This is a rational method problem. And what the rational method states is the rational method is Q equals CIA. It's one of the most fundamental equations that you could ever use in stormwater, and it's always easy to remember because I always remember the CIA. So that one's always really easy. Now, the important thing about the rational method is the units. The units always, always, always have to be the following. So Q is always going to be CFS. C is unitless. That is a unitless number. That's to represent the runoff coefficient. So the higher the runoff coefficient, the more runoff, the less the water actually soaks and permeates into the ground. That's how you can think of it. So that's unitless. Then we got I, which is always an inch per hour. Always. Which, this problem, it gave us an intensity at 6.7 inches per hour. So no unit conversions there. And then finally, A will always be in acres, okay? Acres. So if they gave anything else, we have to make sure that we're converting to these units. Guys, after reading this is a pretty easy problem. You can pause it. You could honestly just run this right in your calculator. I know that if I was given this right on the exam, I probably would just grab this calculator and start multiplying, guys. But since this is all about learning about the tests and learning about the different theories, let's go ahead and write it out. So what are our knowns and what are we trying to solve for? So we're trying to solve for the peak discharge. So we're trying to find Q. So what is Q? Well, what are we given? We're given C. We're given the runoff coefficient, 0.84. We're given the intensity, 6.7. And then we're given A, 3.4. Can be as easy as that, guys. Let's plug this in our calculator and see if we got the right answer. 0.84. We got 19.1. Always understand your units. Rational method will always be CFS. What are they asking for? Cubic feet per second, so we're on the right track. And lo and behold, the answer is D. Guys, pretty straightforward question, right? Will you get a problem like this on the PE exam? Maybe. You might. One way that they might throw you a curveball is instead of just giving you the runoff intensity, what they might actually do is maybe give you a unit hydrograph and you have to determine what the intensity is. Another way that they could do this is maybe they can throw some different units at you and you have to make sure that you're using the right units for the rational method. But that's it, guys. I mean, as a summary, we went through 3 practice problems that you will find on the Water Resources PE Civil exam. I would say that these are fairly straightforward. These are fairly straightforward problems. I think the second problem was probably the most difficult because there were a lot of unit conversions there. But I would say problem 1 and 3 are some of the easier problems that you'll get. Hope you guys learned something new today. I will be making more PE exam prep problems. Feel free to drop some comments below if you want me to address any other topics that you would like. Thank you and have a good day.